This is our last Atwoods Machines Revisited video. These Atwoods Machines problems, they take a while. And so once again, I'm going to be talking rather quickly and going speedily through this. So stop the video, rewind it as you need to, and I will try not to make any mistakes. Here's our situation. We have an 8 kilogram mass on the right. We have a 2 kilogram mass on the left. We have a disc that is a pulley. There's its mass. There's its radius. First, assuming no friction, let's determine V final. If there's no friction, then we don't have to worry about any moment of inertia, and we're going to conserve mechanical energy here. If we say that the initial energy is entirely potential due to this 8 kilogram mass, that means the initial energy is going to be m times g times h, and we can see that this 8 kilogram mass is going to drop a height of 5 meters, and so that would be a convenient place to put the reference line down there. Right before the 8 kilogram mass hits the ground, the 2 kilogram mass, m times g, will have raised up 5 meters. But also at the end, that entire amount of mass, which is 10 kilograms, will have some final speed. This turns out to be 400, that turns out to be 100, and this is 5. So square root of 60, V final. Square root of 60, my calculator says that that is 7.75 meters per second. That's how fast that mass is going to hit once it has dropped 5 meters. What if now there's enough friction between the rope and the pulley to prevent slipping? In the first example, the pulley wasn't rotating at all. Now it is going to be rotating. So now we're going to need to consider the moment of inertia of this pulley. And we might recall, can I fit this at the top? Yes. The moment of inertia for a disc is 1/2 mr squared. What is that going to be? 1/2. The m is 40, and then the radius is 0.5. We need to square that, so that's going to be 5 kilogram meters squared. And when we conserve energy again, which we're going to do, so the initial energy, once again, we're going to say is entirely in the form of potential energy of this 8 kilogram mass. In other words, we're going to make the reference line down here so that the 2 kilogram mass initially has no potential energy. So the entire amount of energy at the beginning is going to be that 8 kilogram mass, m times g times h. At the end, the 2 kilogram mass, again, will have raised up 5 meters. The total 10 kilograms of mass, 1/2 m, will be moving with some translational speed, vf. Now, the pulley is also rotating. So the kinetic energy of a pulley is 1/2 I omega squared. Now, by the bridge equation, omega is V over R. I'll call it V final over R, and R is 0.5 here, and that needs to be squared. So what does that give us? Here again we have 400. This is 100. This is going to be 5 VF squared. And how much is this going to be? That's going to be about 10. 5 divided by 1/2. All right, so that's 15. 30 VF square root of 20. And that looks right. 4.47 meters per second. There we go. All right, so if we rotate that pulley, you can see some of the energy has gone into the rotating of the pulley, so not as much is available for the masses translating. Let's finish up. by saying, hey, if we're told that VF for the masses is 4 meters per second, how much energy was converted into heat? Initially, we're going to say, just like we did, the total amount of energy is in that 8 kilogram mass as potential energy. 8 times 10 m times g times h, which is 400 joules. If we're told that VF is 4 meters per second, what kind of energy do we have at the end? Well, we recall that 2 kilogram mass, m times g, has gone up 5 meters. The 2 and the 8 kilogram masses, that's a total of 10 kilograms, will be moving, we're told now, 4 meters per second. And then that pulley is going to be rotating 1/2 I. We went through on the last page that the moment of inertia ended up being 5 omega squared. And omega is V divided by R. The V is given as 4, and the radius, let me go back for a second, right there, it was given as 1/2 meter, and there in the upper left, there's the moment of inertia being 5 that we calculated. So what does this come out to? This is going to give us 100. That's going to be 16. That's going to be 80 joules. And then how much is this going to be? That's going to be 64 cut in half. So 32 times 5, 160. How's that look? 340. That's how much mechanical energy we have at the end if that's the final speed, 4 meters per second. How much has been converted into thermal energy? 400 minus 340 looks like 60 to me.